Hey everyone, this is Jonathan from Chegg Tutors, and this lesson is about drag, which is the force caused by air or any fluid that an object is moving in, and it acts in the direction opposite of the motion of that object. So what actually causes it? We said it's caused by air, but it's actually caused by, let's say, an object such as a square block is moving downwards and in air, and air is flowing this way. So relative to that object, air is going in the opposite direction. And it's caused by friction between the molecules in air and the surface of that object. So they're kind of hitting the bottom of this object and causing some friction between it and acting as a force that's going opposite direction of the motion. So the actual drag force is caused by the molecules in the fluid, in this case it's air, against the surface of the object. Okay, so now let's move to an example of a brick versus a feather. So I'm going to ask you what falls faster, and you'll obviously say a brick, but I'm going to now say it's in a vacuum. So there's no air molecules, there's no air resistance. So let's draw the free body diagrams for each of these. So we have a brick, and we have our feather. I know it's a horrible drawing, but the only force that's acting if I drop these in a vacuum, the only force that's acting down is mg. It's mass times the acceleration due to gravity on both of them. Now this is the net force, so this force is equal to mass times acceleration, and we can cancel out the masses because they appear on both sides. So we get the acceleration is equal to g. Now this means the acceleration, the increase of the speed of each of these objects is independent of mass. So in a vacuum, a brick and a feather will fall at the same rate. So this is in a vacuum. But what happens in air? Well, in air, we have a brick falling, mg, and it experiences a drag force upwards. We'll call that Fd. And same with the feather, has mg and drag force going up. So the reason in air that a brick falls faster than a feather is due to that drag force, which means that the drag force has much less of an effect on a brick than it does a feather, because a brick just kind of just plows right through the air with really little resistance. And a feather is really affected by the drag force, which makes its descent very, very, very slow. Okay, so now let's take a look at the drag force equation. So we can define all these terms to figure out what this equation is actually saying. This is the velocity of the object. So we see as the velocity gets bigger due to its acceleration, the drag force goes up by the square of the velocity, so it goes up pretty fast. A is the surface area of the object. So if you have a large surface area, there's more surface for the air molecules to interact with, so more surface for friction to occur, and this increases the drag force. Rho here is the density of air, or whatever fluid this object is moving in. So we can call it 1.29 kilograms per meter cubed. So C subscript D is the drag coefficient, which depends on the shape of the object and how it interacts in the fluid. So obviously for a feather, the drag coefficient is going to be much, much greater than it is for a brick, which results in a greater drag force experienced by the feather. And then we just divide this entire equation by 2. So we can see that eventually the drag force will get so big until it equals that downward force due to the force of gravity. And when this happens, our velocity becomes constant. We don't change anymore because all the forces are completely balanced. It's in equilibrium now. And this is what is called the terminal velocity. So let's draw a free body diagram for a square. It's falling at a rate of mg, and it has this drag force going upwards. So at terminal velocity, these two forces are balanced, and the velocity stays constant. There's no more acceleration because our net forces is equal to 0. So Fd equals mg. Again, because the net force is equal to 0 because both forces going in both directions are balanced. So we can say 1/2 CD rho AV squared is equal to mg. So we can solve for the terminal velocity by moving some stuff over, and we get 2mg over coefficient of drag, density of air, and the surface area equals to v squared. And we can get the v terminal is equal to the square root of 2mg or c rho a. And that's how you would solve for the terminal velocity of an object when the drag force is equal to the downwards force due to the acceleration of gravity. So I hope this helped and taught you about drag and the drag force. My name's Jonathan, and I'm on Chegg Tutors.